So we got a couple of different options now to be able to tackle this. We've either got some of the material that we brought up on Monday's class, where we were talking about kind of the power rule and then the reverse power rule, right? The power rule for integration versus the power rule for differentiation. Either of those are fine, or we can do it trial and error, right? Like why don't we play around with some of the options you have? Give me one of the options that it suggests.
One of them is 2 over 3 x cubed plus 10.
Okay, and it's claiming that this is f of x, right?
Yeah.
So it's your choice. Do you want to try to take this equation to this equation through derivatives? Or do you want to try to take this equation to this equation through integrals? Either one is fine. They're literally like one's got to work one way, one's got to work the other way, right?
Yeah. So
Okay, so tell me what you want to do.
integrals.
You want to try doing the integral one. Okay, good. Then we're going to try to start with the 2x squared. And we're going to recognize that if I wanted to do the integral of that, the integral of that should give me something that's similar to this f of x down here. How should we do the integral? What's the methods that we have?
I was thinking the power pattern.
We could use the power pattern, right? Because I have an expression with powers in it. So we're going to try to use the power pattern. All right, talk to me about the power pattern.
Oh, you raise the power and divide it by the same number. So like n plus
Okay,
1.
good. That's going to get what?
X cubed divided by 3. Or 2 over
X
3.
cubed
X 3. Yeah. 2 over 3.
times 2 over 3?
Yeah.
Okay, that looks pretty good, right? It looks pretty close to f of x, right?
Mm-hmm.
So we'll say maybe, right? Kind of looking maybe pretty good.
Yeah.
Right, that's my attempt at like a maybe face, maybe. So nothing immediately violating it. Should we try the other way?
Yeah.
Okay, we'll try it the other way. So now I'm going with 2/3 x cubed plus 10. And I'm trying to take that, I'm trying to look at that through doing a derivative, right?
Yep.
All right, so talk to me about how we could do the derivative of this.
The reverse power pattern.
We could do the other power pattern, right? So we get the other power pattern of differentiation, right? So walk me through that one.
So divide by 3 and then make the power smaller by 1.
Multiply by 3, right?
Oh
It's
yeah,
the
multiply.
opposite of what we did above. Above, we increased the power and then divided. Now we're going to undo that. So we're going to multiply the power and decrease.
Yeah, so it would be 2x squared plus.
Good. So let's bring the power to the front. We multiply by the power. So 3 times 2/3 x, and then we decrease the power. So we go from 3 down to 2, right?
Yep.
Good. What about the next one?
Like what do we do to 10?
Yeah, how do we do it for the 10?
Would it be 30? Just 30, or
Walk me through why.
because you multiply by 3, like to the other one. So
Why
you
multiply by 3? I don't see a x cubed attached to this.
Oh yeah. I don't know.
How many x's do you have here?
0.
You have no 0. You have no x's. Okay, so we can imagine a little 0 here, right? Not entirely precise because we don't want to think about like domain restrictions and stuff like that, but it works out for the pattern. Let's bring the 0 to the front and multiply. What does that get us?
But since it's 0, it multiplies to nothing. Then
Where'd the 10 go?
10.
Still 10?
Oh yeah.
So does this all go away?
Yeah. Because multiply by
Great.
0.
And we're left with?
Wait, what? 2x squared.
Good. Did that work?
Yeah.
Okay. Now let's double. So now what we want to get in the habit of is not just doing the problem, but making sure that we understand why the problem worked that way, right?
Mhm.
So like, let's make sense of, did we understand why the power pattern took us from a squared to a cubed?
Kind of, yeah.
It
Not
can't
really.
be
I
kind of,
just
yeah.
the power pattern.
That, why does the power pattern make sense?
Because we saw as when we were doing the velocity and the speed and all that, we saw like a pattern. So it was like C and
That was much better. Very good, right? So yes, the power increased every time we increased the area. You can think of that like a mnemonic. If you're building area, you're going to build the power. We saw that through examples. We proved it in our notes. The power pattern is legitimate. Got it. That's great. Big fan of that explanation. Does it make sense why the power pattern for derivatives worked out this way?
well, we found out we can undo derivatives into integral. So if you just undo the reverse, just do reverse the power pattern.
So good. Much, much better. All right. And then we go back to our pictures. Did it make sense that the derivative of this expression got us to the 2x squared?
Yeah.
And also notice that like the 10 went away through the derivative. It became plus 0, right?
Mm, yeah.
Does it make sense that 10 doesn't change?
Yes.
I mean, isn't 10 called a constant?
Is it? I'm not sure. Like constant of what?
Isn't that variable plus a constant?
Yeah. Oh yeah. Yeah.
So 10's a constant, right?
Mm-hmm.
Do constants change?
No.
I mean, it's in the name, right? They're constant.
Yeah.
So it makes sense that the 10, if you do a derivative of it, goes away because it's a constant. That's the real reason why the power pattern works for this. And like, it's not about x to the 0th powers, although it does nicely work for these types of problems. So you don't have to like worry about it. But like, it's because it says I have a changing thing plus a constant thing. And if I ask how it changes, the constant thing doesn't change. So the constant thing has no change. The constant thing's change is 0. It goes to 0. And I'm left with just how the first part changed, right?
Hmm.
So
So
now we get to see, okay, so like, what is the function if its derivative is this? This worked out beautifully as a very elegant proof that this is a very good candidate. How we could double check it through the integral is that the integral worked out pretty well. However, we now recognize a truth that I wasn't going to bring up until unit 2. And that truth is it could be this equation with any constant after it. Any constant after this would be okay. Because if I did the derivative of that constant, it would have gone to 0. So it's a matter of saying when we do that integral, there could be a hidden constant in there. We haven't been worrying about it because we've only been looking at how it changes from like bounds of A to B. And when I'm looking at where I am at B versus where I am at A, it doesn't matter how much of a head start I have if I'm just looking for the difference. So I have not introduced that. But here, this is where some of those truths like really start to pop up as you work through the problems. It's like, hey, during one way it didn't work out quite so well, and the other way it did work out quite so well. Like, let's fight for that understanding and realize that like it could have been a hidden plus 10 there, and that would have been okay.
so before since we didn't know that constants disappear in derivatives, the way
Integrals.
integrals, the way we found this as an answer would be just to work out the problem, like like
That's how I
derivatives,
usually find
derivatives.
my answers.
So so if you just did the power pattern to 2x squared, you wouldn't be able to get plus 10, right? Because
Very true, right?
if you
So
know
we
the
start to
constant.
recognize that if you are just trying to do it, because this one did not have anything with like it was asking you for what is the beginning thing if its derivative is 2x squared. We now start to recognize that like if I do a derivative of this, it worked out just fine. So this is a legitimate answer. If I try to do an integral working backwards, I have to remember that there could have been a constant there that also wasn't changing. In other words, this right here is the exact same problem as find f of x if f prime of x is equal to 2x squared plus 0, right?
Yeah.
And we could have said, okay, if you wanted to do that from integration, we absolutely could have done it from integration. This one follows the power pattern, which would be 2/3 x cubed, right?
Yep.
And then it could have been, okay, what is something whose derivative is 0? And you'd be like, it could be any constant number here. That's how we're able to like really reaffirm that like this one makes sense.
Yeah. Okay. Yeah. The only thing I was confused was the plus 10. I'm like, where the hell did that come from? You know.
Yep,
Like,
got to check it, but like we got to dive in, right? It looked like this one worked pretty good, and then we say pretty good, but could there be more? What about through the other perspective? Do I continue to analyze it? Like again, this is where it's like the homework is there to expose and to challenge for it's like if that way didn't work, try another way.
all right. Cool.
Cool.
Yep.
Feel good?
Yeah.
All right, excellent. It's a good exploration. Like this is already like you are actually one of the first people to ask me about this. I'm guessing that everybody else when they solved this problem tried to work backwards through the multiple choice options, which is great. Like right, like that's the path that I taught you all. You chose to work forwards from the problem to the multiple choice possibilities. That's also legitimate. And you found something very inherent, something very interesting, which is that constants don't change. So if you're ever trying to figure out what thing might have made this integral, then we have to consider the constants, which might have derived down to 0.
Mm-hmm. So like, there might be that basically the problem is like 2x squared plus plus 0, right?
2x squared plus, it could be plus 0, right? That's the same idea.
Yeah. All right.
It's literally
Cool.
the same thing.
Yep. Pretty cool.
It is. It is. It's like I said, these are all ones where like, depending on how deep you all dive into these questions versus just trying to get through them, you will be much, much better prepared when I begin to reveal these things to the class than others will, because you always have a path to correctness in the same way that you all have had the ability to do derivatives using the limit definition for a while. Some people recognize there's a power pattern for derivatives as well. And it's like, okay, then they get a little bit of a shortcut in the homework because they were paying attention to the big story, right? And then other people had to mash through the mechanics. And it's like, that will work too. You'll all still get full credit.